Hello, in this lecture, we are going to start with electric field calculations for some of the continuous charge distributions. In this series, we have already done uh, an infinite line of charge. We have done yesterday uh, ring, where we have seen that if charge is uniformly distributed on the ring, and even if it is non-uniformly distributed on the ring, how to calculate the electric field. Okay. So without wasting further time, let us start with a few more questions in this regard. Okay. So the last question that I was yesterday doing, uh, just give me a minute. I'll share the screen. So yesterday we did a question where we actually had a non-conducting ring, and that particular non-conducting ring contained a linear charge density lambda is equal to lambda naught cos theta or lambda naught cos of phi. Okay, and we wanted to find electric field at the center of such a such a ring. Okay, so this is what the question was. Okay, just let me show you the question. So this is how the question was. Okay, so this was the ring, that is, the ring was non-uniformly charged, and the total charge density, linear charge density on this ring was given by lambda naught cos of phi, where phi was the angle from the x-axis. Okay, and if the same question is now asked to you, and instead now if someone says that, okay, let us start with this question only. Let us consider the case of, I'll again consider the case and let you understand. Consider the case of a non-conducting ring. A non-conducting ring. Okay, and okay, so this is a kind of ring here with the linear charge density given by lambda is equal to lambda naught cos of phi. Okay, and what was given to us was, let's say this was our x-axis, this was our y-axis, and this was our x-axis. Okay, let us say this is how it is, and we wanted to find one electric field at the center. So this is what I'm doing, revision from yesterday's class. So just revising what we did yesterday. Okay, consider a non-conducting ring with the linear charge density given by lambda naught is equal to lambda naught cos phi, and okay, so it was this way. So let's say this is an angle phi here, and this is d phi. Okay, and what would be the arc here? This arc is literally r times d phi. Okay, and in the first quadrant, I know that cos phi is positive. So what will happen here? You will have positive charge density, especially near 0 degrees. You will have greater charge density, and as I go along, the charge density would decrease. In the second quadrant, the charge density would be negative, and especially here it will be more dense. Okay, here it will be more dense, and then this charge density would be scattering down, and especially around at 3 pivot, it will not be there would not lie any sort of charge here, basically because the charge density depends upon phi. Okay, since charge density depends upon phi, and here you will have good amount of charge density, and then this charge density will start weakening down as as phi progresses. Okay, now one thing, if you want to calculate the electric field at the center, we need to place unit positive charge at the center. We need to place the unit positive charge at the center. And you see, if I just consider the right hemisphere, or the hemisphere which contains this, I should not say, yeah, you can say hemisphere, not hemisphere, I should say the half of the ring. Okay, this half of the ring. So if this half of the ring contains positive charges, so what will happen if you just take a diameter, just take an opposite symmetrically situated corner. Let's say this is again phi, and this is d phi. So what you'll get that the net electric field will be added in this direction. So let's say this direction is x-axis, so net electric field will be added in this direction. And similarly, if you just see this is a negative, this particular half of the ring is negatively charged, so it will actually attract the unit Coulomb charge. So your dE net would be 2 times dE cos theta. So basically, you just calculate the electric field due to this half of the ring, and I should write phi naught. Okay, from minus pi 2 to pi by 2 and multiply by 2, because see here this particular this particular half ring is giving the net contribution as dE cos phi, and then one needs, since this is negatively charged, so basically this will also attract a unit positive charge effectively in this direction only. So if you can do it using the vector considerations, the same way I have done for the positive side of the ring, you can do it for the negative side of the ring. You will get that net electric field will be in this direction only. So dE net will be 2 times minus pi by 2 plus pi by 2 dE cos phi. And I know what would be dE. So yeah, I'll write first dE. dE will be K dQ. What is dQ? I think it is lambda naught cos phi r d phi. K dQ upon distance would be r square. So I'll simply write r square. Or in other words, K lambda naught cos phi r. No, I'll not even write r. I'll simply write division by r. Okay, so your net electric field integral would be equal to, I'll write E net would be equals to 2 times integration from minus pi by 2 to plus pi by 2. And there you can write K lambda naught, and this will be cos square phi. And I'll write divided by R cos square phi d phi. So it is 2K lambda naught divided by R, and from minus pi by 2 to plus pi by 2. And what is cos square phi? You can write 1 plus cos 2 phi divided by 2 d phi. And eventually, this will give you an answer as simply uh, pi k lambda naught upon r, which is simply lambda naught upon 4 epsilon naught r. And specifically for this question, the direction will be minus of I cap. Okay, the direction will be minus of I cap. So this will be the net electric field. So net electric field will be in this direction. Now you see, instead of this question, if someone asks you slightly different question, and what that question would be, I'm going to just write it. Now, if someone asks you that if this is the case, let us say, I'm just marking it on, right? So, okay, if someone asks you this kind of question and how to do these kinds of question, let us say this is your ring now, okay? Okay, and let us say this is your x-axis, this is your y-axis, then this will be z-axis, and a ring contains the ring contains the charge density lambda is equal to lambda naught cos of phi, where phi is angle, let's say this is how it is. Okay, let's say this is how it is. Okay, this is how it is. Okay, and now you need to find electric field along the axis of the ring, here, which happens to be the z-axis, and let us say at a distance z only. Okay, so let us say we want to find electric field at a distance z. We want to find electric field at a distance z, and the radius of the ring is capital R. The radius of the ring is capital R. Okay. Okay. So see, whenever such questions comes, usually in books also, you'll find such questions being done by symmetric considerations. But at times it is very difficult to understand on which axis the net electric field would lie. So my suggestion would be to use vectorial form of electric field here. So this is my suggestion. So what I'll do, so see, here it is. Let us say the ring is on the, let us say here the ring is actually on the xy axis only. So this is, let's say, y. Let's say this is x. Sorry, this is x. I will write. This is z. This is x axis. This is simply y axis. Okay. Now you see on this particular ring, the total linear charge density is given by lambda naught cos of phi. That implies that the charge density is certainly non-uniform. Okay, so the charge density is certainly non-uniform. So this non-uniform charge density, let us say, let us consider a small differential element here. I think there was a angle was given. Let us say this is x and this is y. X cross y. Sorry, let us say this is x, this is y. Okay, so x cross y would give you z axis. So x cross y. X cross y will give you z axis. Okay, so let us take this angle as phi. Now you see, let us take a small differential element here. This length will be simply r d phi, and the charge contained dq here would be simply lambda r d phi. Okay, another thing is we want to find electric field on the axis of the ring. So axis of the ring would be along the z axis only. Okay, now this is certainly very complicated. Okay, you will not be able to certainly understand. You will not be able to at times. You cannot actually at times. It's very difficult to visualize all these things. So what I do, this, let's say this angle is, let's say this angle is simply theta. So I'll simply write theta and understand this will remain theta only. Okay, this will remain theta only. It is not going to change throughout. Okay, so what I'll do, I'll mark some coordinates for this particular patch, or even, I should not say patch, it's a differential element. I'll mark some coordinates here. So this particular patch, let's say it is on xy coordinate, and the xy coordinate will be simply, see, this is r. So this will be r cos phi. So this will be simply r cos phi comma r sin phi. Okay, so this will be r cos phi comma r sin phi, and let's say this point will be 0 comma 0 comma z. Okay, and what would be this distance? Okay, what would be this distance? So this distance would be simply r cos phi I cap, and let's say this I'm making a direction in this direction. So this is arrow is in this direction. This arrow is in this direction. So okay. So this will be minus r cos phi I cap minus r sin phi j cap if the arrow is in this direction. Take it. Okay, and plus z k cap, and this will be in modulus. So the length length will be in modulus. Okay, so the length will be in modulus. Overall, this particular vector, if I just want to write this particular vector, so if I want to write it this in vector form, so this r vector would be simply minus r cos phi I cap, comma, or minus r sin phi j cap, and then you have this z. Okay, so basically, if I'm writing it in this tuples, in this kind of like in like in form of coordinates, if I'm writing, it implies minus r cos phi I cap minus r phi minus r sin phi j cap, and then plus z k cap. Okay, so we want to find electric field. We want to find electric field, let's say at point P. Find at point P. Okay, so what I'll do, this particular in differential element, in this particular differential element, the charge content is dq, and we want to find electric field at point P. So electric field at point P will be simply k dq. What is dq? It will be lambda r d phi k dq upon this distance ka square. Okay, so I would write r cos phi I cap minus r sin phi j cap plus z k cap modulus. Okay, this is one thing, and it's whole square also. Okay, it's whole square as well. And okay, so this is one thing. And in which direction this particular thing would be? If this is r vector, so I'll write r cap in the direction r cap. Okay. Now you would think if, initially I took some symmetric consideration in the previous question, why I'm not taking it? See, whenever we are going to use vector kind of vector form of electric field, what will happen? The directions will be taken care of by themselves. So don't worry about it. You will be able to understand what I want to say. Just give me a slight minutes. So the differential element dE, that is the electric field due to this differential element at point P, is equal to this. And what would be r cap? Okay, what would be r cap? R cap would be simply r vector divided by r vector ka mod. And what is r vector ka mod? It is equivalent to, so basically, if I want to write modulus of this, so what it will be, modulus of this will be simply, so I'll write it here. Okay. So what is modulus of this? So I'm writing it here. Okay. So modulus of minus r cos phi I cap minus r sin phi j cap plus z k cap. So this is equivalent to writing root over r square cos square phi plus r square sin square phi, which is simply r square plus z square. So it is equivalent to writing k r d phi here and divided by root over r square plus z square ka whole square. And what will be r cap? R cap will be simply r vector. And what is r vector? R vector is minus r cos phi I cap minus r sin phi j cap plus z k cap divided by root over r square plus z square. Okay, this is one thing. So your net electric field differential. Okay, so net electric field in differential form is this, and it is equivalent to writing k r, and then instead of lambda, you will write lambda not cos phi. So it will be like minus r. I'm multiplying cos phi inside. This will be cos square phi minus r sin phi cos phi plus z cos phi k cap divided by, I think it would be r square plus z square, and there would be d phi as well. Okay, so I forgot the d phi. and this will be raised to power 3 by 2, because this is r square plus z square into root over r square plus z square will be r square plus z square e power 3 by 2. If I want to integrate, I'll integrate it. Okay, so your net electric field. Okay, now if you want to cover the entire ring, you have to integrate from 0 to 2 pi. See, whenever you integrate from 0 to 2 pi cos phi d phi, it will always be 0. Why it will be always 0? See, if you want to see integration represents the area under the curve. So if you integrate cos phi, so whatever area is above, in the same amount, there is an area below. So the net area comes out to be 0. And similarly, if you integrate from 0 to 2 pi, similarly, if you integrate from 0 to 2 pi, sin phi d phi, it will also come out as 0 only. Sin phi cos phi d phi, it will also come out as 0. So basically what will happen, if you just see this integration, this is along the z cap. So this integration would go to 0 if I integrate from 0 to 2 pi. And this integration also would go to 0, because if cos phi is integrated with respect to d phi from 0 to 2 pi, it will be 0. Only one component would remain alive, that is along the I cap. So this is k r lambda naught, and there's another r here. So there would be r square instead, divided by r square plus z square raised to power 3 by 2. And similarly, minus would be there, and this would be cos square phi d phi, integration from 0 to 2 pi. Okay, so your net electric field will be equivalent to writing minus k lambda naught r square upon r square plus z square raised to power 3 by 2. And what is cos square phi integrations? Cos square phi is 1 plus cos 2 phi. And again, remember, integration from 0 to 2 pi, cos 2 phi is also 0. Okay, so okay, now you see, if I integrate from 0 to 2 pi cos square phi d phi, what you will get? You will simply get it as pi. Okay, you can integrate this up and you will get the answer. So cos square phi, if I write it as 1 plus cos 2 phi upon 2 and integrate, I'll get simply pi. And this is I cap. And if I want to take the magnitude part of it, if I just want to write the magnitude part of it, the net electric field will be in the x direction, and that will be simply lambda naught. And this is 1 upon 4 pi epsilon naught. So there is a pi here, and pi gets cancelled. So basically this is 4 epsilon naught r square divided by r square plus z square raised power 3 by 2. And if this distance is quite large, that is, we want to find electric field at a distance z which is very, very greater than r, then the answer would be simply net electric field in that particular case is simply lambda naught r square divided by 4 epsilon naught z cube. This is that simple. Okay, so I hope this question is quite clear to you. So this brings us to the end of this particular lecture, and in the next lecture we are going to do a few more questions. Till then, take care.